Good day, guys. First of all, my name is Clifjan Ginovo and my partner Jan Jelan Abolok, and we are going to tackle about the emerging technologies that may help power the future.
There are 12 types of emerging technologies that may help power the future. The world human population is already more than 7 billion, a number that could exceed 11 billion by 2100, according to projections from the United States nations. This rising population coupled with environmental challenge puts even greater pressure on already strained energy resource. Granted, there is no silver bullet, but Georgia Tech researchers are developing a broad range of technologies to make power more abundant, efficient, and eco-friendly. This picture provides a quick look at a dozen annual projects that could go beyond traditional energy technologies to help power everything from tiny sensors to home and businesses.
Type of emerging technologies is NATECC Word is Salt. Shannon Yee, an assistant professor in Georgia Tech's George W. Woodruff School of Mechanical Engineering, is developing a technology that leverages the isothermal expansion of sodium and solar heat to directly generate electricity, affectionately known as NATECC, an acronym that combines the chemical symbol for sodium with initials from thermoelectrochemical converter and also rhymes with GATEC. This unique conversation engine has no moving parts. A quick rundown in geek speak: electricity is generated from solar heat from thermally driving a sodium redox reaction on opposite sides of a solid electrolyte. The resulting positive electrical charges pass through the solid electrolyte due to an electrochemical potential produced by a pressure gradient, while the electrons travel through an external load where electric power is extracted. Bottom line, this new process results in improved efficiency and less heat leaking out, explained Yi.
Second is new breed of voltaics. In another project, Yes Group is using nuclear waste to produce electricity, minus the reactors and sun's moving parts. Founded by the Defense Advanced Research Project Agency, DARPA, and working in collaboration with Stanford University. The researchers have developed a technology that is similar to photovoltaic device with one big explanation. Instead of using photons from sun, it uses high energy electrons emitted from nuclear byproducts. Flexible generators. Yes Group is also pioneering the use of polymers in thermoelectric generators or TEGs, solid-state device that directly convert heat to electricity without moving parts. TEGs are typically made from ignoratic semiconductors. Yet polymers are attractive materials due to their flexibility and low thermal conductivity. These qualities enable clear design from high-performance devices that can open without active cooling, which would dramatically reduce production costs. The researchers have developed P and N-type semiconductor polymers with high-performing ZT values and efficiency metric from thermoelectric materials. We'd like to get to ZT values of 0.5 and we're currently around 0.1, so we're not far off yeast.
Type is recycling radiowaves. Researchers led by Manos Tenet series have developed an electromagnetic energy harvester that can collect enough ambient energy from the radio frequency spectrum to operate devices from the Internet of Things (IoT), smart skin and smart city sensors, and wearable electronics. Harvesting radio waves is not brand new, but previous efforts have been limited to short-range systems located with meters of the energy source. Explained Tenzeris, a professor in Georgia Tech's School of Electrical and Computer Engineering. His team is the first to demonstrate long-range energy harvesting as far as 7 miles from a source. Fifth type is picking up good vibrations. In another energy harvesting approach, researchers in Georgia Tech's School of Mechanical Engineering are making advances with piezoelectric energy, converting mechanical strain from ambient vibrations into electricity. Scientists have been exploring this field for more than a decade, but technologies haven't been widely commercialized because piezoelectric harvesting is very case and application dependent, explained Alper Ertork, an assistant professor of acoustics and dynamics who leads Georgia Tech's Smart Structures and Dynamical System Laboratory. Current piezoelectric energy harvester rely on linear resonance behavior, and to maximize electrical power, the excitation frequency of ambient sources must match the resonance frequency of the harvester. Even a slight mismatch results in drastically reduced power output, and there are numerous scenarios where that happens, Ertork said.
Power up the right way. Triboelectricity enables production of an electrical change from friction caused by two different materials coming into a contact. Although known for centuries, the phenomenon has been largely ignored as an energy source because of its unpredictability. Yet researchers led by Zhong-Ling Wang, a Regents Professor in Georgia Tech School of Material Science and Engineering, have created novel triboelectric nanogenerators or TENGs that combine the triboelectric effect and electrostatic induction. By harvesting random mechanical energy, these generators can continuously operate small electric devices. First thing debuted in 2012, powered by foot tapping, and generated enough alternating current the power banks of leads. Since the researchers have been pushing the envelope on their technology and have developed a self-charging system that not only converts alternating current to direct current but also feature a power management unit that adapts to the variability in human movement. Optical retina. Researchers led by Baratunde Kula, an associate professor in Georgia Tech School of Mechanical Engineering, have developed the first non-optical retina, a technology that could be more efficient than today's solar cells and less expensive. Retinas, which are part antenna and part receptor, convert electromagnetic energy into direct electrical current. The basic idea has been around since the 1960s, but Kola's team makes it possible with nanoscale fabrication techniques and different physics. Instead of converting particles of light, which which is what solar cells do. We're converting waves of light, he explained. Key to his technology are antennas small enough to make the wavelength to light about 1 micron and a super fast diode achieved in part by building a antenna on one of the male in the diode. Kula described it process. Cola nut tubes are grown vertically of a subretinate. Second, using automatic layer diffusion, the non-tubes are coated with aluminum oxide to serve as an insulator. Third, extremely thin layers of calcium and aluminum metals are placed on the top to act as an conduit.
Type is pulp energy. Although fossil fuel emissions may be the poster child of global warming, there is also growing concern over environmental harm from discarded electronics. Researchers at Georgia Tech's Center for Organic Photonics and Electronics COPE and Renewable Bioproducts Institute are developing paper-based electronics, organic solar cells, organic light emitting diodes, OLEDs, and organic field effect transistor fabricated on cellulose-based substrates that can be recycled easily. Use of paper to substrates has generated considerable buzz among researchers, but its high porosity and surface roughness pose challenges to today's organic electronic components use very thin carbon-based semiconductor layers, about 1,000 times thinner than the average human hair. Because they are so thin, you need nearly atomically flat substrates where the surface is down to nanometer. Type is fuel from the sky. Another intriguing project. Researchers led by Peter Lutzenhisser are leveraging solar energy to reverse the combustion process and produce synthesis gas, mixtures of hydrogen, carbon monoxide, and small amounts of carbon dioxide, which can be converted into fuels such as kerosene and gasoline. Instead of using fossil resources to create fuel, we are using the byproducts of combustion, water, and carbon dioxide to re-energize the system with the sun, explained Lutzenhisser, an assistant professor of Georgia Tech's School of Mechanical Engineering.
Then, hello graphene supercaps, goodbye batteries. Used in everything from military applications to inventors and cars. Supercaptures an attractive source for clean energy because they quickly change and discharge and have long cycling lives. But there's one big drawback: low energy density. Today's supercapacitors have only one tenth the energy density from lithium batteries, pointed out Leo, a Regents professor in Georgia's Tech Schools of Materials Science and Engineering. For the device to give you the same electrical energy, the device would have to be much bigger. Working with C.P. Wong, another Regents professor, Leo is developing graphene-based supercapacitors that offer significantly increased energy density which maintaining high power and long operational life. The research is funded by ARPAE. Monolithic microscale heat pumps, providing that good things come in small package. Researchers led by Cernivos Garmilla have developed a novel textbook-sized cooling system that operates on waste heat rather than electricity. The underlying technology has been used in very large-scale installations such as hospitals and universities campus, explains Garmella, a professor in Georgia State School of Mechanical Engineering. Yet, his team takes the science to a new level by working at the microscale and creating a self-contained unit. Gene power plants. Researchers in Georgia State School of Mechanical Engineering are working on major makeover for power plants, introducing innovation that range from removed power cells to new infrastructure materials. In one project, steam is being replaced with supercritical carbon dioxide or CIO ECO2 as the working fluid to operate turbines and produce electricity.
Pasarang tami, ma'am.
ACCO2 results when carbon dioxide is substituted to pressure about 7.4 megapascals and temperature above 31 degrees Celsius. This magical state, somewhere between a liquid and a gas, provides high fuel density, thermal conductivity, and heat capacity. ACCO2 is currently used in environmentally friendly dry cleaning and coffee decaffeination. In energy application, its high density and compressibility will enable generators to extract more power from turbine, explained Divish Ranjan as an associate professor of fluid mechanics. Equipment could be made from top-notch materials, yet dramatically smaller, which would reduce production costs.
The goal is to reach heat to electricity conversion efficiency of more than 45%, a substantial increase when compared to 20% efficiency for a car engine and 30% for most sources on the electric grid. The technology could be used for distributed energy applications. An ATECC engine could sit on your backyard and use heat from the sun to power an entire house. Yi said, it can also be used with other heat sources such as natural gas, biomass, and nuclear to directly produce electricity without boiling water and spinning turbines.